Our final question. I want to share with you, why is it that we have multiple ways to assign a variable? Because in Python 3.8, we gained another operator, the so-called walrus operator, under PEP 572 assignment expressions. Remember, if we have a Python object, we can customize certain parts of that Python object. We can customize, for example, what it means for that object to be equal to something else. And we saw that. This is one of the reasons why just because something is identical to something doesn't mean it's equal to something. Because you can customize EQ however you want. You can return false all the time, like float NaN does. You can do whatever you want. But you cannot customize the is check. Is handled at an interpreter level. This always checks, are the IDs equal? It always does. In the case of CPython, are the pointers that these PyObject references contain, are they actually the same pointer? Another thing you cannot customize in Python is the assignment operation. This is handled in the bytecode. It's handled by the interpreter. There is no such thing as a copy constructor or any of those mechanics in Python. This thing cannot be overloaded. X equals 1, 2, 3 can never change in its behavior. It always says, in this particular scope, assign the name binding of 1, 2, 3 of X to the object 1, 2, 3. There's no way to customize this. Now, let's take a look at all the syntaxes, all the relevant syntax we have. Say we have two structures. X is Y says, are X and Y the same underlying object? Meaning, if I change something via the name X, will I see that change via the name Y? Is this a live view or is this a snapshot? And you do that all the time with your NumPy and D arrays. You want to ask them, are you a view or are you a copy? X is Y asks, are you a view or are you a copy? Are you the same object or not? X equals Y, well, that's more of a kind of operational question. Are you considered to be equivalent to each other using whatever you consider to be the notion of equivalence? And so in the case of two lists, that is, do you have the same values in the same order? In the case of two sets, do you have the same values irrespective of the same order? You might wonder why it is that we still have collections.order dictionary in Python, even though the Python dictionary post 3.7 is guaranteed to be ordered. Well, the reason for that is if you have two Python dictionaries and you want to see are they equal, that is customizable. And it is customizable like any other Python equality is customizable. Here, if we have these two dictionaries, A, B, and let's actually make them equal here, with A and B here, and these two ordered dictionaries with A and B here, you can see one of the meaningful differences between the ordered dictionary and the dictionary is their notion of equality. For the regular dictionary, they're equal if they just have the same keys and the same values, irrespective of their ordering. But for the ordered dictionary, do they have the same keys and the same values in the same order? And you can think this actually corresponds very closely to real problems that you have because, for example, in JSON comparison is independent of the order of the keys. JSON does not specify an ordering for the keys. So if you had a dictionary that was representing some JSON data, you probably want this. Whereas, and obviously, in practice, you can't always make that assumption, but in terms of what JSON specifies, you're not really guaranteed what the order is. But in XML, the nodes are ordered, and so you want this because it matters the order in which the nodes occur. So you can see there's actually a very fine distinction here. Well, setting that aside, we know that this syntax here says make X another name that refers to the same object that Y refers to, and it always means that, and it can't mean anything else, but X and Y now refer to the same underlying object. Here is the new syntax that was added. Make X another name to refer to the same object as Y. And let me use Y at the same time on the same line of code. For example, one of the examples used to motivate this is we have some regular expressions. And we want to loop over these regular expressions and find the one that matches. So we'll start with some really tight ones, then we'll go to some loose ones. We'll match exactly A, B, C, D, E, F, or we'll match A, B, D, E, F, or we'll match A, and then something in the middle. And we want to capture the parts that didn't match as part of our capture groups. We could write this as a for loop, iterating over these, and looking for the first one that had a full match, then breaking out of this loop and printing out the result. And so you can see this matched the first regular expression this matches no regular expression, this matches the second regular expression, and this matches the third regular expression. But if we didn't have this in a for loop, if these were if we didn't have these in a structure, these are independent entities, this is how we'd have to write it. First, create the match object and see if it matched. If it didn't match, create another match object and see if it matched. And if it didn't match, create a match object and see if it matched. Because we can't write this. If we wrote this, it wouldn't be the first match. It would, for the broadest pattern, it would match all of them. And so here, if we wrote something like this, you can see it would match all of them. So here, if we want the exclusive match, we either have to do a loop, which we can break out of, or we have to have these very ugly nested chained if-else. But with the assignment expression, which means, broadly, I want to do something, and I want to look at it at the same time. I want to do something, namely an assignment, that's what this is, and I want to look at it at the same time. And so here, you can see, do the assignment and look at it at the same time. Let's see if we can get the syntax right. Here, do the assignment and look at it at the same time to see if it's a non-known object. Here, do the assignment and look at it at the same time. And once we write this, you can see, oh, these are actually now exclusive. So we can now nicely flatten this. We can nicely linearize this. And this is a big benefit to our daily code. Now here's a question. Why does it matter? Because for all of the questions we've covered, it's not the goal that we want to cover the trivialities. The syntax by itself doesn't matter. There's oftentimes many ways to do things. Find one, solve your problem, move on with your life. Why does this matter? It matters because when you really dig deep into the thinking behind this, it gives you insight in whether these tools are actually appropriate for your use case, when they are appropriate, and what they can gain you in your code, and what they can tell you about programming in general, even beyond Python. This matters because there are many circumstances where you want to do something and you want to make use of it at the same time. And I want to show you something else that looks totally different. But before I do it, I'll show you a place where this comes up very often. Here I have an xarray data array. And my xarray data array has some coordinates and some dimensions. And I definitely want to avoid, especially if I'm live coding, that I make mistakes when I'm doing something here. So here I'm going to say, oh, the dimensions of this thing, this is an image, so it's dimensions y and x. And you know what? When I'm live coding, doing something like this is too error prone because I'm just going to jam on the keys. So what I'll do is I'll use my unpacking syntax. So here I have dimensions y and x for this xarray. And I want to give this some coordinate system as well. So I want to give this a coordinate system where x is drawn from a linear space from 0 to 10 with 3 samples. And y is drawn from a linear space 0 to 10 with 3 samples. So 0, 5, and 10. Then I'm going to say, you know what, let's prototype this a little bit further. Let's make this 5 by 5. Oops, this broke. We didn't have enough coordinates. So let's update this here and here. That's getting kind of unpleasant. I don't want to write this on 2 lines. Why don't I get a very temporary binding to this data, and then down here I can say data.shape of 0, and I can say data.shape of 1. I can eliminate some risk of update anomaly. And here you can see on the same line, where line means one unbroken Python expression within the same expression, which usually is one line, one expression, I can do something, perform an assignment, and make use of it, including if that assignment is to a keyword argument. But here's where this is a more general pattern beyond just the assignment expression. Let's say I have a pandas data frame. And pandas data frame is dates, entities, and values. I've gone out and I've got some data on a time series with some entities, and I have some values, and I want to do means and sums and averages and whatnot. And every time I use pandas, I always remember to take care of my index. So I'm going to set my index to my date and my entity. Okay, that looks good. If I'm going to set my index, I might as well sort my index so that if I do subsequent group bys, those group bys can see that the index knows it's monotonic and can make use of that monotonic index so I don't do a redundant sorting. Okay, that's good. Once I do that, what I'm going to do is I'm going to select from this, I'm going to select just some of these entities. So I'll do an index slice, and I'll select just some dates and just some entities. And you know what? I want every entity except the entity ADA. So what I'll do is I'll select from the 3rd of February to the end, and I'll select every entity except ADA. And I know I can do this as an index operation. I can do like an index subtraction. So what I'll do is I'll do df.index.getLevelValues of entity, and I'll say compute the difference with ADA. And this gives me all the remaining things from that index, except it blows up in my face. That requested level doesn't exist. What do you mean? Come on, I just said it 2 lines ago. On this line, I want to make use of the thing that I did while I'm in the process of doing it. And so, this is why lock with the lambda exists in pandas, so that I can make use of the data frame that may have had operations occur between the last time it was assigned to and when I'm seeing it here. Remember, in the previous one, this df here doesn't mean whatever the result of this operation was, because those weren't in place, those were making copies. It means this thing up here. And so lock with the lambda, that's what it means. And let's say I want to do something to the axis here. I want to do something, maybe I'm going to take the axis and I'm going to round them to the nearest month. Here, I'm going to do a set axis. And I'm going to do a set axis. I'm going to set the axis to a multi-index generated from, and I probably need multi-index imported. I'm going to do a multi-index generated from the arrays. And the arrays that I'm going to give it are whatever the original index looked like. So df.index.getLevelValues, date, and the entity. And up here, I'm going to do something to this. So maybe I'll do a .floor, and I'll floor it to the month. But this will break. These don't exist except as part of the chained operation. Set axis doesn't take a lambda, but the more generalized one is pipe. And this is why pipe exists. If you think about it, pipe, lock with the lambda, assign, if you do something like assign signal equals lambda df value, and you do maybe something like divided by df value. This is maybe the normalized value. All of these things, here, here, and here, all of them. And let's round this to the nearest here, because I want a fixed that's not a fixed frequency. Let's round this to the nearest 2 days. There we go. Or let's round this to the nearest 7 days, because I want to see some difference there. Whatever the case may be, what you can see here is anytime you want to perform an operation and look at it at the same time, it's all the same pattern. Lock with the lambda, assign with the lambda, pipe with the lambda, the assignment expression, all of these are the same underlying pattern, and this is what we hope that you got from this session.